Hello dear students, today's lecture is based on free damped vibration numericals as per the comments in previous lectures by the students regarding they want to study more numericals based on this free damped vibration. So we will solve more example based on this. So moving further for the process. So today's numerical statement is an underdamped system shock absorber is to be designed for a modern mass of 100 kg such that during the road bump the damped period of vibration is harmonic and the amplitude of vibration should reduce to 1/6 in 1 cycles. Find number 1 spring stiffness, number 2 damping coefficient of the shock absorber. Okay, so first of all data is given to you. Okay, so m is equal to 100 kg, t4 is equal to time period is given to you 2 seconds, and there is a condition. Okay, amplitude is 2 seconds and the amplitude of vibration we can see here should be reduced to 1/6 in 1 cycle. So it is x1 by x2 is equal to 16. Okay, 1/16 in 1 cycle it is reducing over a vibration. Okay, so here we have to define two different things. First is the spring stiffness and second is the damping coefficient of the shock absorber. Okay, so first of all their mass is given to you and time period is given to you. Okay, so first we have to define the natural frequency. Okay, so first we have defined here is the damped frequency omega d is equal to 2 pi divided by t. So it is 3.142 radian per second. Now this condition is given to you x2 is equal to x1 by 16. जो फर्स्ट एम्पलीट्यूड है उससे 1/16 रिड्यूस हो रहा है एक साइकिल कंप्लीट होने के बाद. सो बिटवीन फर्स्ट एंड सेकंड साइकिल देयर इज अ रिडक्शन इन एम्पलीट्यूड ऑफ 1/16 दिया गया है. ओके, सो इट इज वी कैन से दैट x2 is equal to x1 divided by 16. दिस रिलेशनशिप is given to you in the example. Okay, so by applying the equation of logarithmic decrement delta is equal to log e base to x1 by x2 we can directly find out the value of here, because here it is 1 minus n, so 1 upon 1 number of cycles is 1 here. So it is आगे जो 1 upon n था वो अभी इधर नहीं लिखा हुआ है हमने. Why? Because it is 1 by 1 it is 1. So it is delta log e base to x1 by x2. So we can directly get the value of this delta logarithm. It is 2.773. It is unitless term. Okay, so same way by using the relationship equation of the relationship between zeta damping factor and delta logarithmic decrement we can find out the value of zeta here. Okay, now there is one more important equation. It is omega d is equal to under root of omega n under root of 1 minus I square. मैं आपको लिख के दिखा रहा हूँ. ओमेगा d is equal to omega n under root of 1 minus zeta square. This is the equation. Okay, it is the relationship between damped frequency versus natural frequency. There are two frequencies here, natural frequency and damped frequency. Okay, so this is the relationship between that omega d is equal to omega n under 1 minus zeta square. So from this equation we can directly find out the value of natural frequency omega n. So this term omega d and this equation of omega d is new for you. We have not used this equation previously. Okay, so remember this equation is very important. So after finding out omega n, we can find out the value of stiffness by using the equation omega n is equal to under root k by m. Okay, so by applying the equation of zeta c divided by cc, we can directly find out the value of c. Its unit is Newton second per meter, जो हमने previous example में भी देखा था. Okay, तो ये इस तरह से example में हमको क्या करना है. Once you have to remember the equation of omega d. It is the relationship between omega d, omega n and zeta, means damped frequency, natural frequency and damping factor. This is the relationship between these three parameters. Okay, so this way we have to find, first we have to find stiffness k, then this zeta. By using of the zeta equation we are finding the damping coefficient c is equal to 277.44 Newton second divided by meter. Okay, so if you have any doubts, please write in the comment section. Okay, thank you so much.